Guys, so we're going to do our second installment of Unit 11, which is air pollution, and we're going to still focus in on some of the major air pollution problems. In this case, we're going to namely talk about thermal inversions, and then we'll be talking a little bit about ground level ozone some more, along with the destruction of stratospheric ozone. I'm going to pick a different color. Red's just too harsh at the moment. All right. So the reading that goes with this, hopefully you guys already read page 608. There's a little section on thermal inversions in there. And then section 19.7, pages 621 through 624 is the portion on ozone. Okay? So we'll talk first about thermal inversions. So we're going to go back to our profile of the atmosphere, but we're going to focus in again primarily on the troposphere and stratosphere today. In the troposphere, you guys should remember that with altitude, temperature decreases. That is the normal temperature profile in the troposphere. It does something different in the stratosphere. Kind of goes back and forth like that we talked about earlier this year. But the troposphere, as you get higher altitude, as you work your way up in the atmosphere, there is a general cooling pattern, right? And there's several physical reasons for that we won't get into. Okay. Now, as the name suggests, when there is a thermal inversion, right, we actually end up with a little pocket of cool air, right, and then some warmer air sitting on top of that. Okay, that's essentially what a thermal inversion means. So air temperature gradient is altered due to a persistent cool layer of air that remains near the surface. Now, you guys should be familiar with this if you spent at least a few years in Walla Walla. You've been through those periods of time where we get locked into sometimes weeks on end persistent fog, where it's maybe 27 degrees at night, and then during the day it might get up to a whopping 29 degrees Fahrenheit, and it just stays, right? That fog just stays, and the temperature just remains cold, and doesn't change very much, right? That's because in Walla Walla we are prone to some thermal inversions, particularly in the wintertime. Okay, now, what does this have to do with air quality? Well, it sort of has to do with what we call air stagnation, right? So when we get this persistent pool of cool air stuck at the surface, right? Reason that happens, because cool air is denser than warm air, so it makes sense that it settles down in these valleys, Walla Walla being a valley. All right, Salt Lake City is another example where they get a lot of thermal inversions. Okay, this cool air settles in this valley, and a layer of fog often builds up, which sort of prevents the sunshine from penetrating and heating up the surface and heating up that lower parcel of air, right? And it usually is due to the fact that there's an intense kind of like a high pressure system, which means we have sinking air, which means we're generally not going to have any wind, right? So basically there's no wind. That causes that pool of air to just kind of get stuck in these valleys, right? And there's not a whole lot of mixing. And so the pollutants, so in our more densely populated areas, Walla Walla, for example, is not super densely populated, so we don't end up with the absolutely horrible air quality we might end up with in somewhere like Salt Lake City. But we do end up with some air stagnation and air quality advisories during this time. Right? But basically, the mixing of our air is greatly reduced because we have this stubborn pool of cool air that's just not moving, and the pollutants just kind of work their way up into that little cool pool, and they just don't move from there. Okay, and over time, those pollutants build up, and we end up with some really poor air quality. So the way you could look at an inversion temperature profile, so we might still see some decrease with altitude, right? Then we have this layer of warm air on top of it, right? And then another decrease. Now, sort of a side note, this is not exactly air quality related, but when we get freezing rain, this is often the atmospheric temperature profile we have, right? So kind of picture this really stubborn, cool pool of air, right? And if a system moves in, I'm going to go back to red here just because it's going to work better for showing warm air. But if a warm, moist system moves in, right, that warmer air gets pushed up on top, right? Okay, and so this might be where our precipitation clouds are, right? So the air, the moisture might start off as snow. It falls through this warm layer, turns into water, right? And then hits this cold layer again, which is probably often below freezing. And so what it does is it's a liquid, it falls through this cold layer, and then when it hits the surface, it refreezes again in the form of ice, and that's why we get freezing rain occasionally. So even though it might be, 22 degrees at the surface, right, we have this warm layer in between where our precipitation falls and the surface. That precipitation melts and it refreezes when it hits the ground, and that's why we get freezing rain instead of snow during those times. All right, now, so that's a thermal inversion. You guys just need to remember what happens to our temperature profile and why that is related to poorer air quality often. All right, now moving forward to ozone, right? We're going to focus in on stratospheric ozone initially. Okay, so stratosphere, remember, is the second layer of our atmosphere, and this is our good ozone, because that's what protects us from the nasty rays coming from the sun. So primarily we're talking about ultraviolet energy, right? So we have visible light, right? And then just above that is our ultraviolet light, a little bit more energetic and thus more able to cause damage to our tissues, primarily our skin. So it comes in three varieties. There's UVA, UVB, and UVC. This is, so UVC is the most energetic, UVA would be the least energetic of those three. All right, and the way ozone essentially works, without getting too much into it, different molecules in the air are good at absorbing different wavelengths of light. So if you guys recall way back to climate change and the greenhouse effect, carbon dioxide and water vapor and methane and nitrogen oxides are pretty good at absorbing infrared energy. Ozone is actually really good at absorbing ultraviolet energy, and that's actually very good for us because that stuff could really hurt us. So pretty much 100% of the ultraviolet C is absorbed up in the stratosphere. Most of the UVB, about 90-ish% of that, is absorbed up in the upper atmosphere. But a lot of the UVA is actually able to penetrate through, which is why we still are in danger of sunburns and damage from sun if we're outside for too long without either a sunscreen on or UV protective clothing. Okay? So UVC is our most energetic. Darn near all that gets blocked up in the upper atmosphere, thank goodness, because that would be really damaging to us. UVB is mostly blocked. UVA. Now, if you ever look at your sunscreens, they usually say UVA and UVB protection. That's what they're talking about. They're saying that sunscreen is specially formulated to filter out both ultraviolet B and A. All right. Now, normal stratospheric ozone formation. It is a cycle. Oops, excuse me. So we start with, we're in the upper atmosphere, up in the stratosphere where there's still plenty of ultraviolet light. And what happens is we can take some ultraviolet C, is able to break apart our oxygen molecules. And I hope you guys remember, right, that, so we have an O and an O here for O2. Oxygen is our second most abundant molecule in the atmosphere. So ultraviolet C, so it's got enough energy, right, to split those oxygens apart into single oxygens. Okay, so O2 is our most stable form. O, just single oxygens, very unstable. Now, what can happen when we have these single oxygens is, first of all, they can just link back up again to form O2 again. Or, if there's a single oxygen and some other oxygen molecules nearby, right, they will link up to form O3, which is our ozone. Now, in order to get to split apart our oxygen molecules, we have to have that super energetic ultraviolet C, right? Ultraviolet A and B will not generally split apart oxygen molecules. Ultraviolet C is able to do that. Because there's still plenty of ultraviolet C working its way through the atmosphere up in the stratosphere, we're able to split some of our oxygens apart. Right? Some of those single oxygens, which are really, really unstable, will then latch on to an O2 molecule to form O3, right? And that is our ozone. Now, the ozone molecule is even better at absorbing ultraviolet C and ultraviolet B. Right, so now if we have an O, 1, 2, 3, right, we can split that apart. So then we're back to O2 and oxygen, and that might form up with another oxygen, or they might recombine to O3 again, and we kind of got this ongoing cycle of O2 to O, O3, and then back to O2 and O again, right? And then we can just keep that cycle going on and on and on. Now, because there is ultraviolet C up in the upper atmosphere, right, we get, being stubborn here, this layer of increased ozone formation. And way up there in the stratosphere where there's no organisms to be harmed by it, right, it's actually doing us good because it filters out a lot of those nasty types of ultraviolet light. Okay, so if we insert some CFCs, CFC stands for chlorofluorocarbons. Now they are a really stable compound we used to use in refrigerants and aerosol sprays and air conditioners and things like that. And essentially what they look like is a carbon in the middle with some chlorines and fluorines attached to it in some sort of combination. All right. Now, CFCs are extremely stable down here in the troposphere, which means when they get into the atmosphere, they do not break down. And it was thought for a long time that that's perfectly fine because our really, really stable molecules like chlorofluorocarbons were thought to be not harmful at all. They really just kind of want to hang out in the atmosphere. We could breathe them in, breathe them back out, and not really know the difference. Plus, they were such a small portion of our atmosphere. They just were not problematic, or so we thought for a really long time. Okay? And they thought they were a great substitute for like our original refrigerants like methyl chloride and ammonia, which are pretty harmful. Okay? So we've got these CFCs in the atmosphere. Now, because they're so stable, they were actually able, through air currents and stuff, able to work their way up to the stratosphere. All right? Now, if we take our really stable CFC molecules up to the stratosphere, remember we have some highly energetic sunlight in the form of ultraviolet B and C, right, that can actually begin to degrade those CFC molecules. And it turns out that when these CFC molecules degrade, they can wreak havoc on the formation of our helpful ozone layer. And I'll kind of explain what that process looks like. So we start with a CFC molecule, right? So what happens, again, up in the upper atmosphere, we have ultraviolet C. That can come in, right, and essentially break or degrade that molecule. So we might get a free chlorine, all right? So like our single oxygens, our chlorines, when they separate off, are considered chlorine radicals, and they're really unstable. Right? So anything in chemistry then, is something that's unstable is going to react with something nearby as quickly as possible. So what happens is those free chlorine molecules can then, if they bump into an ozone molecule, they'll essentially pull that apart, right? So the free chlorine attacks an ozone, is going to form oxygen gas and a chlorine oxide. Okay? Now what we have is, instead of an abundance of ozone molecules, right, we've got reduced ozone, put a little down arrow, and these chlorine oxides. Now, we talked earlier about we're still having oxygen molecules, right? So an O and an O being split up to form single oxygens. And it's the presence of those single oxygens in and around an abundance of O2s that make that ozone, right? Now, if I take a single oxygen, right, but it bumps into a chlorine oxide instead of an oxygen, right, we're going to form O2, and then we're going to have that single chloride again. Okay, does that make sense? So form O normally, so chlorine oxide is going to break down ozone to form chlorine oxide and oxygen, right? That chlorine oxide might bump into a single oxygen to form O2 and chlorine, and then that chlorine is able to then go back in and attack. So a single chloride radical can continue to break down molecule after molecule of ozone. Okay, so what we have to understand here is we're reducing the amount of ozone in two ways. The first way is we're breaking ozone apart with those chloride radicals, okay, and we're preventing the formation of new ozone because there's an increased abundance of these chloride oxides that can reduce the likelihood that a single oxygen forms ozone instead of just O2. Now, that is a problem simply because O3, ozone, is much better at absorbing ultraviolet light than O2 is. Okay, so what we likely get with the thinning of the ozone, so if our ozone thins, we're likely to get an increase in the amount of ultraviolet B that penetrates the atmosphere. All right, so we're going to do some more chemistry here shortly, but basically what we have is ozone formation in the troposphere. So this is what we have. We call this bad ozone. So down here where we can breathe it and it can get in our eyes. So remember, ozone is one of those primary components in photochemical smog, both an eye and respiratory irritant. So how do we get ozone in the troposphere? So the way that happens is we have some some nitrogen oxides, right? So vehicle exhaust, so coming out of these tailpipes, if we burn nitrogen gas in the presence, if we burn something with oxygen in the presence of nitrogen at too high a temperature, we're going to get nitrogen monoxide. All right, now this is a really common thing that forms in and around cars, and again, it's one of those pollutants that is regulated by the Clean Air Act, so our exhaust systems have to do something to reduce nitrogen oxide emissions, and this is primarily why. Now, if we have some nitrogen oxides, and we put that in the presence of oxygen gas, we're going to form nitrogen dioxides. Okay, now what's the trouble with nitrogen dioxide other than it's a primary? Okay, so the nitrogen oxides are a primary pollutant. They can form things like nitric acid, right, which is contributing to acid rain. But we recall earlier, even with our protective ozone layer up in the stratosphere, we still get some ultraviolet light that gets all the way down to the surface. Now, if I combine some nitrogen dioxide with some highly energetic ultraviolet light, excuse me, that's the wrong symbol. Okay, so that's our UV. Okay, what can happen is we're going to split that back apart into nitrogen monoxide and a single oxygen, and as we know, those single oxygens are highly unstable. If we combine that single oxygen with an oxygen molecule, we're going to get ozone formation. So why do we get ozone formation in the troposphere? We get it because of an abundance of nitrogen oxide pollution, primarily coming from our vehicles. So Ozone formation in the stratosphere is good. It's a natural phenomenon. It can be broken down by the abundance of CFCs, right? Ozone formation in the troposphere is bad, and it forms because of an abundance of nitrogen oxides, primarily from our vehicles.